Hello everyone and welcome back to my channel. In today's videos we're diving into one of the most interesting, exciting frontiers in technology, and this is quantum computers. We'll start by looking at the quantum computer stock that hit the New York Stock Exchange in 2024 and 2025. You'll see a major surge that began at the end of the last year and continue into early this year, with some stocks increasing tenfold. We'll also explore the key highlights from NVIDIA 2025 conference, including a major statement from the CEO, Jensen Huang, who said that we have reached an inflection point in building quantum computers. That comment triggered the sharp rise in quantum stocks at the beginning of this year. Rigetti, D-Waves, and other companies, some of them climbing nearly 10 times. Next, let me start the video which I prepared to you. At the beginning I have some cards which we're going to review very quickly. We'll walk through those card topics right now, breaking down the top computer companies, some major players like IBM, Google, and Intel. We'll tackle the big question: is now the right time to invest in these companies? As Jensen Huang was actually saying, buying into those companies may be the next big thing within the next 5 to 10 years. Some of these computer companies might grow to rival where NVIDIA is today, while NVIDIA itself could start to feel like a thing of the past. So this is for this introduction. Let's jump in.
Investors have also been bullish about the technology's future, with some quantum computing stocks rallying over 1,000% in 2024.
I have prepared this portfolio named Quantum. You'll see in here a number of companies. Some of them are well known to you, like Google, Alphabet, IBM, and Intel. The other are companies which you don't know so well: Rigetti, D-Wave from Canada, Quantum Computing. A characteristic for all these companies is that you will see the minimum amount of a share for this year was less than $1, and right now it's around $20, $27, $19. This is the maximum, or $54. So let's open one of those companies. I'm going to open D-Wave, and you'll see that in October and before that in September it's actually $1 or less than $1, and after that it shoot up to $15, $16.39, which is the price for today. The same is true for other company. This one, IonQ, actually last year it was $7, and right now the maximum for this year is $54. If we look for several years back, you'll see that in 2021, at the end of the year, it was that company reached a maximum of $24. After that it went down, and it stayed pretty much down up to November 2024, September, November 2024, when it went up to the value which you see right now on the screen, $45. The reason for that evolution of the price is the fact that the CEO of NVIDIA, Jensen Huang, in 2021-2022, he expressed an opinion that quantum computers were going to be probably available in 15 to 30 years, and that made the price go down. Recently, at the end of last year, beginning of this year, he changed his mind, and his comment was that the quantum corporation and building quantum computers reach an inflection point, meaning that we are very close to use the quantum computers to solve real problems which cannot be solved by classical computers. In April 2025, at the beginning of this year, at NVIDIA Technical Conference, a number of companies were invited, and the CEO or development director, development of research from those companies, had a discussion on a stage with Jensen Huang from NVIDIA about the future of quantum computers. I would like you to listen to a short fragment from this conference.
Anyways, that was just my swing at it. Go ahead, Peter.
Well, here at the show, we are actually have several applications which are showing quantum as now. One of them is with ANSYS, and you might know one of their products, which is LS Dyna, and runs obviously with GPUs today. We announced that we've integrated our quantum computers with LS-DYNA and a 12% increase in performance in modeling a blood pump. And so this is the first, I think the first time actually quantum with production software. We also announced with NVIDIA, AWS, and AstraZeneca a 20x improvement in a chemistry application. What's amazing about it is that we did that on 36 qubits, our existing system today. By the end of the year, we will have 64 qubits. Every time you add a qubit, you double the computational power. So that's 2 to the 28 increase in a single generation of chip, which is roughly 260 million times more powerful. So by the end of the year, one would expect for things like LS-DYNA and for chemistry applications to suddenly have huge performance increases. And so we're working right now on these applications, which, to be honest, probably all of you use, to now be able to have significant impact using a quantum computer. I do think that your statement about 10 years is, we think of ourselves as like 10 years, where you were 10 years ago. We hope that obviously 10 years from now, we'll be up there with NVIDIA as well in a rarefied club. So, but it does take a long time to go from, it's kind of a startup to where you are today. And it's completely fine to sit down and say for the computer industry, for the quantum industry, it's going to be another 10 to 15 years to get to where NVIDIA and all the other giants are. It's just not going to start then. It's starting today.
You're going to be much, much larger than NVIDIA. There's no... We're going to be a relic of the past.
Scroll down on the YouTube video from NVIDIA Technical Conference and take this list of panelists from the description and you add it into the ChatGPT. You will find out additional information so you can see the public and the private companies. The majority of those companies building quantum computers are actually private companies. I will stop the video here because it will continue with the presentation from Dario Gil. I'm trying to be careful not to get into it, but you see that the majority of those companies are actually private companies, but it's a little bit difficult to find out which will be the winner. That's why I'm concentrating on major companies, major corporations, especially like IBM. I have listening to presentation by Dario Gil, which was years ago Vice President of Research at IBM, and recently, for a number of years probably, he's actually the Director of Research, and I was interested in quantum technologies, and his presentation are actually amazing. You will see a few fragments coming up next. Dario Gil explaining that the time of building quantum computer is now. It was a few years back. They started their roadmap in 2016. They have a roadmap from that moment up to 2033, and they are close to deliver a major milestone in 2029, which we'll discuss about it. So for now, let's listen to Dario Gil, and the time for building quantum computers, it is now.
And a major character in the film is a professor from Stanford. And at the beginning of the film, he said something that really captivated me. He said the thing that differentiates scientists is a purely artistic ability to discern what is a good idea, what is a beautiful idea, what is worth spending time on, and most importantly, what is a problem that is sufficiently interesting, yet sufficiently difficult that it hasn't yet been solved, but the time for solving it has come now. So I want to tell you about this beautiful idea whose time for solving it has come now. And that is the possibility to create quantum computers. To give you this unease that you should feel when you talk about quantum information and quantum computing, I'm going to give you a very simple example, a thought experiment that also happens to be true. So let's imagine that we're going to solve this problem. The problem involves you have 4 cards. 3 are identical, 1 is different, 1 is a queen. We shuffle the cards and we put them face down, and the problem we're going to solve together is find the queen. we're going to be assisted by two computers. One is a classical computer, one is a quantum computer. So what we do is we turn them down and we load them into memory. So we use 4 memory slots. The cards are identical, we put zeros. The one that has a queen, we put a 1, right? So in our 4 slots, we'll have 3 zeros and 1 is a 1. We load them on the 2 computers. Now we ask to write a program to find the queen, find the 1. How would it be done classically? You would go and pick a random number, you don't know where it is. You go, look under that memory slot, see if it's a 1. If not, you go to the next slot, and so on and so on. On average, it would take you the equivalent of 2.5 turns to find it. It turns out that with a 2-qubit quantum computer for this problem, you can always solve it in one shot. So that uneasy feeling that you have now should be an explanation that quantum computer is not just about building a faster computer, it is building something that is fundamentally different than a classical computer.
At this moment of the video, I would like to discuss just a little bit about quantum physics and quantum computers. So, quantum physics was actually established at the beginning of the last century, 1920. The major names was Niels Bohr, of course Einstein, Heisenberg, more recently other people like Richard Feynman, which is really famous. And the way it's actually working, why quantum computers are completely different, is that in a classical quantum computer you have 2 states represented by 0 and 1, right, binary state. But into a quantum computer, quantum physics has a couple of properties which is used by quantum computers. One is called superposition, and the other one is actually entanglement of atoms. And the superposition means that for the calculation, they are not use only 0 and 1, but all the intermediate value between 0 and 1. So probably, if my understanding is correct, it's an infinite number of vectors which are creating some probability. And the result, it's a single measurement which is collapsing the wave function, and at the time when you are collapsing the wave function, because you are able to manipulate your error code and understand that you are close to an answer. At the time when you are collapsing, actually the quantum function, you are getting exactly the result. Right, so this is how quantum computers are actually working into a very high-level kind of explanation. And again, this is my understanding. I will let the video talk a little bit about it. And after that, Dario Gil will present a few real-life scenarios when quantum computers it's actually needed. What are the type of problems which are not able to be solved with quantum computers at that moment in time? So let's listen to it.
That takes Willow under 5 minutes would take the fastest supercomputer 10 to the 25 years, or a timescale way longer than the age of the universe.
Like classical computers, which store information in bits, with each bit representing either a 1 or a 0, quantum computers use quantum bits or qubits, which can exist in superposition of 1 and 0, meaning they hold multiple possibilities simultaneously. Qubits can also be entangled, where the state of one instantaneously affects the other, no matter the distance. These properties enable quantum computers to solve certain types of problems exponentially faster than classical systems.
So there are a large number of problems in the world that have this characteristic that they blow up exponentially. And a dirty secret in the world of computing is that we obviously talk a lot about all the things that computers can solve, and can solve a lot of things. But then there's a lot of things that computers cannot solve. And very interestingly, they cannot solve it now, nor ever. And the reason is because they have this exponential built into them. So take as an example this fairly simple equation, factoring. So if I have a number m that is made out of the multiplication of two large prime numbers, and I only give you M, and I ask you, find me P and Q, it turns out that that is phenomenally difficult to solve. There's no other way but to divide it sort of sequentially by prime numbers. So, in fact, it's so difficult, we use it as the basis of all encryption. But if you had a very large universal fault-tolerant quantum computer, which is many, many years away, you could solve that problem in seconds, what would take billions of years in a classical computer. That tells you something about the power of what is going to be possible. Take chemistry as a problem, because it also has this characteristic that it blows up exponentially if you try to calculate it. This equation that you see here is very interesting because it's predicted to occur at the ocean floor near volcanic sites, and famously it's been hypothesized to be the basis of the formation of life on Earth. But if you take a molecule like iron sulfide and you try to do relatively simple calculations with a normal machine, it turns out that we're not very accurate. And the reason is that molecules form when electron orbitals overlap, and the calculation of each orbital requires a quantum mechanical calculation. So for that simple molecule, you have on the order of 76 orbitals, and 2 to the power of 76 is intractable with a classical computer, so we cannot solve it. Again, on this theme of our assumptions that computers solve everything, but they don't, if you look at calculating, for example, the bond length of a simple molecule like calcium monofluoride, we still get it off by a factor of 2, even using the larger supercomputers in the world. To me, this has been very interesting, this recognition of all these problems we cannot solve. It's also true in optimization problems that are the basis of logistics and routing and portfolio optimization. There's tons and tons of problems in which at best we do approximations, but we're far from optimal because the number of possibilities is enormous. So I'll close with Feynman, who proposed this original idea of creating these quantum machines, and his inimitable style, he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Thank you.
The major players into quantum computer worlds are actually the company you see on the screen: Intel, Amazon, IBM, and Google. You can see that each of these corporations started development years ago, 2015 for Intel, Amazon 2019, IBM early 2000 research and development, and major push from 2016. You will see a roadmap from IBM going up to 2033. Google started in 2009, in-house from 2014. Google claimed they achieve quantum supremacy, and that was happening last year when they have created a new chip called Willow. And IBM is trying to achieve quantum advantage. And what are actually those two things? I have tried to Google to use ChatGPT to get this information, and I have it right at the bottom. So give me a second to find it out. Okay, so you see quantum supremacy, which Google claim they were able to achieve. A quantum computer beats a classical one at any task, even if useless. In quantum advantage, a quantum computer outperforms classic system as a useful real-world task. Like you see, Google 2019. So I'm not 100% correct. I'm not correct, right? Because I said last year, it's in reality 2019. Their quantum computer solved a random sampling problem in 200 seconds that would take classical computer thousands of years. But the problem itself had no practical use. And the quantum advantage, it's a future goal. Quantum systems solve a chemical simulation optimization problem or machine learning task better than any classical approach. That's the real value. And the next clip we're going to show some of those development coming from Microsoft, coming from Google, and at the end I will concentrate on showing you the roadmap from IBM and presenting a little bit more about their plans, because I really followed them for a long time, and in my mind they are probably a very serious company which are making plans over 20-30 years and are going ahead and trying to complete them. So by 2029 and 2033 you'll see that IBM have a major milestone to achieve. So let's listen to it.
Qubits. There are neutral atom qubits, there are trapped ion qubits, and then there are other qubits which you see a little bit less industrially.
Google, IBM, Amazon, and Rigetti Computing are all betting on superconducting qubits, while Xanadu and PsiQuantum use photonic qubits. In February, Microsoft announced that it had created a quantum computing chip, Majorana 1, that uses a new type of qubit known as a topological qubit. The technology required the creation of a new state of matter that could make quantum computers more resilient to noise and shorten the technology's development timeline from decades to years.
Now, as far as we have come, and we shared almost exactly 2 years ago, right, the first development roadmap, where you saw the progress in terms of system modularity, in terms of number and quality of the quantum processors, but we also shared the software stack, from kernel developers to algorithm developers to model developers. And as far as we have come, we've also reached the conclusion that for the next wave of the roadmap, we needed to think even more ambitiously, and that we needed to go back to the drawing board and imagine the next generation of technology, of systems, and quantum. And that is something that we're also very proud now to be able to share with you. Because to enable this to happen, we need a new system. And a new system that is designed with modularity at the heart of it all. Because to create systems that are going to have tens of thousands of qubits, that are going to need to orchestrate classical and quantum resources in a new way, we needed to expand the range of possibilities. And that is IBM Quantum System 2. And what you're seeing here is how we're going to bring it to life. We will have a much larger system of refrigeration in there, such that we can fit within a single cryostat systems now that will have even thousands of qubits within one. But importantly, the modularity is designed throughout. Not only inside how we are going to bring together different quantum processors, but importantly, the fact that multiple systems are going to be able to be connected to one another. So in these configurations of 2 and 3 systems, and in the future even expanding them further within the context of a quantum-centric supercomputer, where we will see connections that range from classical connectivity to quantum mechanical connectivity in terms of communications. So one of the things that the team is creating and designing is the convergence of communications and computing in the field of quantum. This is an enormously ambitious idea of how we're going to bring classical and quantum information with modularity, with very large systems where communication and quantum computing are coming together. So with IBM Quantum System 2, we're already building and designing it. And our objective is to be able to instantiate and deliver that first system 1 year from now.
IBM has spent nearly a decade honing its vision for quantum advantage and large-scale fault-tolerant quantum computing. And now that vision is coming into focus. In 2026, we will see the first demonstrations of quantum advantage. And in 2029, we'll enter into a new era of computation with the first large-scale fault-tolerant quantum computer. We know exactly how we'll achieve it, and we're updating our roadmap to match. Let's take a look. Today's IBM Quantum Roadmap is really 2 roadmaps in one. Our development roadmap tracks production systems and software tools to enable advantage for end users, and our innovation roadmap tracks experimental work and prototypes that inform production hardware and software, and our journey to fault tolerance. Let's start by looking at how our development roadmap lays out the path to quantum advantage. Last year, we released the IBM Heron, which demonstrated significantly improved gate performance thanks to its tunable coupler architecture and the ability to accurately run circuits with 5,000 gates. We believe advantage will occur in the next few years if we continue to push our hardware performance and couple it with high-performance classical computing. To facilitate that effort, we're excited to announce a new processor coming in 2025, the IBM Nighthawk. Nighthawk introduces a new square lattice of 120 qubits targeting 5,000 gate circuits. It delivers roughly 16 times the effective circuit depth we can achieve with the heavy hex lattice of its predecessor.
So I would like to show to you the roadmap up to 2033 because the previous video was cutting short before that. And you will see that the major milestone I was talking about before is 2029, when IBM will deliver a fault-tolerant quantum computer with the ability to run 100 million gates on 200 logical qubits. And after that, in 2033, quantum computers will run circuits comprising a billion gates on up to 2,000 logical qubits, unlocking the full power of quantum computers. And I heard before that those number of gates are actually the number of operations. So from 100 million to 1 billion, it's a huge increase, so just in few years. And the first fault-tolerant quantum computer looks to me like a computer everybody can use, or at least the major corporations which are trying to solve some of the problems. I heard in one of the presentation from IBM that at that current moment they are working with 300 companies, and they have around 500,000 users which are using the quantum computer they currently have. So if you look back a little bit, you'll see that we are in 2025, and whatever IBM was able to build so far, it's around 120 qubits, 133 qubits with 5,000 gates. So that's the explanation, or adding a little bit of more information to the previous video. And moving next, I will talk, and this will conclude the video about the IBM share price and how the stock performed this year, which it was a great surprise for me as well. Just wanted to show to you how the stock for that corporation is actually performing. I haven't invested recently in IBM. I always had it in the back of my mind. I have to take a look at it. And recently, while I was investigating it, I realized what a good stock it is, right? This year alone, it went up 64%. And if you look over the number of years, pretty much it's going up, right? So for some time in here, 2013 to 2022-23, maybe not a lot of movement, but from that moment on, look at this line. So I have look at the financial situation, the cash flow, which I like to try to understand. 5 billion net income. If you look in here, there are a few interesting things. I've seen that they do a lot of cash acquisition, 10 billion, right? So all those numbers which they look negative, it's actually money invested in acquiring other corporations. Some of this, it's actually related with the stock market. Let's see, investing in marketable and equity security, which is around $2 billion, right? So all of this money is actually not wasted, and really capital expenditure is only 1 billion out of how many? 5, and so on, right? So the numbers look very good. Huge company, like all those companies, Microsoft and so on, they are very aggressive and laying off people whenever they feel they need to do that, and they are investing on the long term, artificial intelligence and quantum computers. So definitely a company to keep an eye on. Dividend, they are doing okay, 2%. So we have reached the end of the video. I hope you guys enjoy it and the information is useful to you. Keep in mind to look after those stocks and consider investing if you think it's a good idea for the future. If you enjoyed this video, please consider subscribing and hit the like button. It's not only helping the channel grow, but it will help me supporting myself into the future for a retirement income. That's my dream. But even if this is not happening, it's good if you guys were able to find some good, useful information you can use. So until next week, when I will probably create a different videos for you to take a look at, I wish you all the best in everything you do. Have a good weekend, and goodbye, guys.